Welcome back to the deep dive. Today we're tackling, well, probably the biggest shift ever in how we understand the universe, Einstein's general theory of relativity.
It's a big one, all right. And we're
Yeah.
going deep, not just talking physics concepts, but really trying to shift that fundamental view of gravity.
Right, moving it away from Newton's idea of a mysterious force pulling things across space.
And towards Einstein's view,
Mhm.
gravity is just a feature of geometry, the shape of space-time itself.
And the sources we're working from today, this excellent set of educational materials, really lay it out clearly.
They do. And we should acknowledge up front the clarity and the organization owes a lot to the contributions of educator Hasiai Valid Toran. Really helpful structure.
Absolutely. So our mission today is to help you make that leap with Einstein. Forget gravity as a force. Think geometry.
And when we're done, you'll hopefully really grasp how mass warps space, how that affects light, and maybe the weirdest part, how it changes the flow of time itself.
It sounds mind-bending already. Okay, let's start with the foundation, the equivalence principle. Where did Einstein begin with this?
Well, it starts with a thought experiment, actually a couple of them. The core idea is simple. Locally, you cannot tell the difference between being accelerated and being in a gravitational field.
Okay, break that down. What's the scenario?
Right. So first, imagine you're in a closed box, say a spaceship, way out in deep space. No planets nearby, engines off, you're just floating, weightless.
Total zero G. Got it.
Okay, now second scenario. You're in the same box, but this time it's falling freely towards Earth. Maybe in an elevator with a cable snapped or just orbiting. Inside that falling box, what do you feel?
Well, I'd be falling too, so weightless again. If I drop my keys, they'd float next to me.
Exactly. Inside the box, the experience is identical. Floating in space or freely falling, you can't tell the difference without looking outside. That's key. Free fall feels like zero gravity.
So Einstein is saying free fall is like the natural state. It cancels out gravity locally?
Precisely. It's not that gravity disappears. It's that you are moving along the natural curve of space-time caused by Earth's mass. You don't feel a force because you're following the path of least resistance, the geodesic.
Okay. But how does acceleration fit in? That seems like the opposite.
Right. So third scenario, back in deep space, far from gravity. But this time, your spaceship's engines are on, accelerating you upwards constantly, say at 9.8 meters per second squared.
Ah, the same acceleration as Earth's gravity. So I'd feel pushed down onto the floor. I'd feel my normal weight.
You'd feel exactly the same pressure on your feet as you do standing right here on Earth. Indistinguishable.
So if the feeling is the same, and the laws of physics inside the box have to work the same way in both cases,
Then gravity and acceleration must be, in some deep sense, equivalent manifestations of the same underlying reality. Gravity isn't some spooky force reaching out. It's a local effect tied to the curvature that mass creates, which dictates acceleration.
and that explains Galileo's old observation. Why everything falls at the same rate, feather or cannonball, ignoring air. It's not about the object's mass. It's about the path through space-time they're all following.
You got it. The path is dictated by the geometry, not by the object, which leads us straight into something really radical. What this means for light.
Right. Light has no mass, so Newtonian gravity wouldn't really affect it much. Maybe a tiny bit due to energy equivalence, but with this equivalence principle.
Let's go back to that accelerating rocket.
Mm-hmm.
Okay, constant acceleration upwards. Now, you shoot a laser beam straight across the cabin from left to right. What happens?
While the light is traveling across, the floor is accelerating upwards.
Exactly. So by the time the light hits the other wall, the wall has moved up slightly. To you, inside the rocket, that perfectly straight beam of light appears to curve downwards, hitting the opposite wall lower than where it started.
It looks like it's falling, like a ball thrown sideways.
It follows a parabolic path, yeah. Because your reference frame, the rocket, is accelerating.
Okay, so if acceleration and gravity are equivalent.
Then light must also follow a curved path in a gravitational field.
Wow. So it's not that gravity pulls on the light beam.
No. It's that the mass of, say, the sun warps the fabric of space-time around it. Light, just like anything else, follows the straightest possible path through that space-time. But in curved space-time, the straightest path isn't straight in the way we usually think.
It's a geodesic, the shortest path on that curved surface, like drawing a straight line on a globe.
Perfectly put.
Yeah.
And this wasn't just a theoretical idea, it was testable. Einstein calculated exactly how much starlight should bend as it passes near the sun.
And his prediction was different from the old Newtonian one.
Significantly different, about twice the deflection, actually. Because Newton's theory didn't account for the curvature of space itself, only a sort of weak gravitational pull on light's energy.
And this led to the famous 1919 eclipse expedition. That was a big showdown, right?
Absolutely. Arthur Eddington led expeditions during a total solar eclipse. The idea was simple. Simple in concept. Photograph the stars visible very close to the edge of the sun during the darkness of the eclipse.
And compare their positions to photos taken when the sun wasn't there.
Exactly. If space-time is curved by the sun's mass, those stars should appear slightly shifted outwards, away from the sun, because their light had to bend around it to reach us.
And did they?
They did. The measurements were difficult, but the observed deflection matched Einstein's prediction from General Relativity, not the Newtonian one. It's huge news. Front-page headlines worldwide. It basically confirmed that Einstein's geometric view of gravity was correct.
Okay, so gravity curves space. And you mentioned space-time is one thing, so does it curve time too?
It absolutely has to. If space is warped, and space and time are interwoven into space-time, then time must also be affected by gravity. This leads to gravitational time dilation.
Time dilation, meaning time runs differently depending on gravity. That sounds like science fiction.
It does, but it's real and measurable. The core idea is, the stronger the gravitational field, the slower time passes relative to a region with weaker gravity.
So like time literally ticks slower closer to Earth than it does further away.
Yes. Even small differences in altitude create tiny but detectable differences in the rate of time. Take two identical, hyper-accurate atomic clocks. Put one at sea level and one on top of a mountain.
The one on the mountain is in slightly weaker gravity.
And it will tick slightly faster. The clock at sea level, deeper in Earth's gravitational well, runs just a tiny bit slower. We can measure this difference today. It's not theoretical anymore.
That's pretty wild. So my feet are aging slightly slower than my head.
Technically, yes. Infinitesimally slower, but yes, the effect is real.
Okay, if time itself is stretched or compressed by gravity, what does that mean for light trying to escape a massive object, like climbing out of that gravitational well?
That's where gravitational redshift comes in.
Yeah.
Think about the light leaving a star. It originates in a region of strong gravity, where time runs slower. As that light travels outwards, uphill against gravity, into regions where time runs progressively faster, it has to lose energy.
Why does it lose energy? Is it like friction?
Not friction, no. It's because of the time difference. Imagine the light wave like a series of crests. If the crests are emitted from a region where time runs slow and observed in a region where time runs fast, the observer sees those crests arriving less frequently than they were emitted.
Ah, lower frequency means lower energy for light.
Exactly. Slower frequency means a longer wavelength, shifting the light towards the red end of the spectrum. That's the redshift. It's direct evidence that gravity affects the flow of time, which in turn affects the energy or color of light climbing out.
And this isn't just some weird astronomical thing, is it? I heard GPS relies on this.
It absolutely does. It's crucial. GPS satellites are orbiting far above Earth, where gravity is significantly weaker than on the surface.
So their clocks run faster.
They do. By about 45 microseconds every single day compared to clocks on the ground. It sounds tiny, but GPS relies on nanosecond timing accuracy. If the system didn't constantly correct for this gravitational time dilation predicted by general relativity,
The whole system would fail.
within minutes,
Yeah.
your calculated position would drift by kilometers every day.
That
So yeah, every time you use GPS, you're relying on Einstein's understanding of curved space-time and slowed time.
really brings it home. Okay, so this theory wasn't just predicting new things like light bending and time dilation. It also had to explain existing problems, right? What about Mercury?
Yes, the perihelion precession of Mercury. This was maybe the first great triumph of general relativity, solving a puzzle that had baffled astronomers for decades.
What was the puzzle exactly?
Mercury has an elliptical orbit, not perfectly circular. The point in its orbit where it's closest to the sun, that's the perihelion, isn't fixed in space. The whole ellipse slowly rotates, or precesses, over time.
Okay, that happens with orbits. What was the issue?
The issue is that Newtonian gravity, even when accounting for the pull of all the other planets, couldn't quite explain the amount of precession observed. It predicted most of it, but there was a tiny discrepancy left over,
How tiny?
about 43 arcseconds per century. An arcsecond is tiny 13/600th of a degree, but it was persistent, measurable, and unexplained by Newton's laws. People even invented a hypothetical planet, Vulcan, inside Mercury's orbit to explain it, but it was never found.
So how did Einstein's weird geometry fix this very precise orbital mechanics problem?
Because Mercury is the closest planet to the sun, it's moving through the most strongly curved region of space-time in our solar system. General relativity says that this very curvature of space near the sun adds an extra little nudge to the orbit that Newtonian physics, assuming flat space, just doesn't account for.
It wasn't a missing planet, it was missing geometry in the equations.
Exactly. When Einstein applied the equations of general relativity to Mercury's orbit, they predicted precisely that extra 43 arcseconds of precession per century. It matched observation perfectly. No fudge factors, no missing planets, just the geometry of space-time.
That must have been a huge confidence boost for the theory. It didn't just predict strange new things, it fixed old problems too.
It really cemented its place as a superior description of gravity, especially in strong fields.
Let's talk a bit more about that geometry. You said positively curved. What does that actually mean for space itself?
Well, think about Euclidean geometry, the kind you learn in school on flat surfaces. Angles in a triangle add up to 180 degrees, parallel lines never meet, etc.
Right, standard stuff.
In the positively curved space near a massive object, like the sun or a black hole, those rules break down. If you could somehow draw a giant triangle in space around the sun, the sum of its angles would actually be more than 180 degrees.
Like drawing a triangle on the surface of a sphere.
Exactly like that. That's positive curvature. So space itself near mass behaves less like a flat sheet and more like the surface of a ball. The geometry is fundamentally different.
And that warped geometry dictates how things move. The straightest path idea.
Precisely. Mass tells spacetime how to curve, and spacetime curvature tells mass and light how to move along those geodesic paths.
Okay, if massive objects curve spacetime, and those objects can move, like stars orbiting each other, does the curvature move with them? Can it ripple?
Yes, that's the next huge prediction. Gravitational waves. If you have accelerating masses, especially very massive objects moving very fast, like two black holes spiraling into each other and merging, or two neutron stars colliding, they create disturbances, ripples, in the fabric of spacetime itself.
Like dropping a stone in a pond, but the pond is the universe.
That's a good analogy.
Yeah.
These ripples travel outwards from the source at the speed of light, carrying energy and information about the event that created them.
Einstein predicted these way back, didn't he? But they were incredibly hard to detect.
Extremely hard. The distortions they cause by the time they reach Earth are unbelievably tiny, stretching and squeezing space by less than the width of an atomic nucleus over kilometers. For decades, they were purely theoretical.
Until LIGO.
Until LIGO, yes, the Laser Interferometer Gravitational Wave Observatory. In 2015, LIGO made the first direct detection of gravitational waves, coming from two merging black holes over 1 billion light-years away.
Wow. 1 billion years ago.
And the signal they detected matched the predictions of general relativity perfectly. It was the final major piece of Einstein's theory to be experimentally confirmed. It opened up a whole new way to observe the universe, not with light, but with gravity itself.
What an incredible journey. From thinking about elevators to detecting ripples in space-time from colliding black holes. We've really shifted from gravity as a force to gravity as the dynamic shape of reality.
It's a profound shift. We've touched on the core ideas. The equivalence principle, linking gravity and acceleration, how that leads to light bending, the warping of time itself, time dilation and redshift, and finally, the idea of space-time as a curved dynamic geometry that even ripples with gravitational waves.
It fundamentally changes how you have to think about space, time, and motion.
It really does. Einstein's insight, starting from that simple idea about freefall, gave us this incredibly powerful and accurate description of the cosmos. It's all about the geometry.
So here's a final thought to leave you with. If gravity is just curvature, and we know even climbing a few flights of stairs means your personal clock ticks infinitesimally faster than someone on the ground floor, what does that really imply about time? Is your now truly simultaneous with the now of someone just slightly deeper in Earth's gravity well? Something to ponder.
Indeed. And understanding these concepts, seeing how they build from the equivalence principle onwards, has been made much clearer thanks to the excellent structure provided by the source materials, acknowledging again the valuable contribution of Ashai Veli Turin to this body of knowledge.